Alright guys, welcome again to Supplement Tutorials. Today we'll be talking about iron deficiency anemia. In our previous videos, we talked about the various types of anemia we have. We talked about the microcytic hypochromic anemias, of which we mentioned some examples like anemia of lead poisoning, iron deficiency anemia, the thalassemias. And then we also touched on the macrocytic anemias, that's the vitamin B12 deficiency, the folate deficiency, and so on. Today our focus is going to be on iron deficiency anemia, and I hope you enjoy the video. So we are going to talk about the definition of anemia. We are going to talk about the body distribution and transport of iron. We're going to talk about iron absorption. We are going to talk about iron requirement, the causes of iron deficiency anemia, some clinical features we might find in iron deficiency anemia, then some laboratory findings. Then we'll talk about dimorphic films, then bone marrow iron. Alright, let's get started. So, when we talk about iron deficiency anemia, first thing that we have to know is that iron deficiency anemia is one of the two major differential diagnoses of microcytic anemia. So, two major differential diagnostics for microcytic anemia. And what are the two major differential diagnoses of microcytic anemia? So we have iron deficiency anemia, and then we have the thalassemia. So what you have to know is that iron deficiency anemia got to do with the hem aspect of the hemoglobin, whereas thalassemia has to do with the globulin aspect of the hemoglobin. Okay, so what happens in iron deficiency anemia is that there is a reduction in iron. There's a reduction in iron. It could be a reduction in iron. It could be a reduction in iron. So it could be reduction in iron. In iron, it could be reduction in iron absorption. It could be reduction in iron transport. It could also be a reduction in iron storage. So all these can contribute to iron deficiency anemia. So as the word goes, iron deficiency anemia, there's a deficiency in what? In iron. Alright. So basically that is the definition of iron deficiency anemia. When we talk about iron deficiency anemia, what you have to think about is that it's got something to do with the hem portion. And remember, it is iron moiety that we find in what? In the hem, in order for us to get our hemoglobin. So without the iron, that's the ferrous form of the iron, Fe2+, there's nothing like hemoglobin. So we need the iron. So once this iron is deficient, that is where we find ourselves to have iron deficiency anemia. Alright, so let's go to the distribution of and transport of iron. So first of all, iron has to be distributed in the body. So after absorption, assuming the body has finally absorbed the required iron, that is the ferrous state, Fe2+. Fe2+. Now, the iron has to be what? Transported and then stored and also received. So when we talk about transport, storage, and then reception of iron, these are the three molecules that we encounter: transferrin, ferritin, and then transferrin receptor 1. So let's talk about the transferrin. All these ones are protein molecules that is found in the plasma. So let's talk about transferrin. So transferrin is a protein molecule that is capable of transferring two atoms, approximately two atoms of what? Of iron. Approximately two atoms of iron. So normally during hemoglobin synthesis, it's the transferrin that is responsible for the transfer of what? Of plasma ion to the cells, so that hemoglobin synthesis can be made possible. So that is what we have to take notice of, transferrin. So if someone has a deficiency in transferrin or a problem with the transferrin, it means the person will not get, although the person will have ferrous ion circulating in the body, but those ion will not be able to be transported to the cells for hemoglobin synthesis to what? To occur. So transferrin is a very important molecule. Now let's go to ferritin. Ferritin. So ferritin is actually the stored form of iron. Basically, we have two main stored form of iron. We have ferritin, then we have hemosiderin. Hemosiderin. And the difference between the two is their solubility in water. So we have ferritin being soluble in water, and then hemosiderin being non-soluble or insoluble in water. So ferritin and hemosiderin are the stored form of what? Of iron. So when there's excess iron and then there is a need for the conversion into what? Into a proper state, then the iron has to be converted into what? Into ferritin. So that when there is a demand for iron, the ferritin will now be converted back to the ferrous ion for hemoglobin synthesis to be what? To be possible. Now the last molecule we are going to talk about in the distribution and transport of iron is the transferrin receptor 1. So when we take the hematopoietic stem cells, especially those that got to do with red cell production, so let's say erythropoietic stem cells, they have numerous transferrin receptors. Okay, because before transferrin will be able to transport the ion to the intracellular compartment of the cell, it has to bind to a receptor. And once there is a presence of what? Of transferrin receptor 1, it means there's going to be what? A proper interaction. There's going to be a proper interaction between the transferrin and the cell through the transferrin receptor, so that the ion will be able to be transported smoothly to the intracellular compartment for hemoglobin synthesis to occur. So this is what you have to take notice of. Transferrin for the transfer of ion or transport of ion. Ferritin is a stored form of ion, and transferrin receptor 1 is what? A receptor protein that is found on erythropoietic stem cells or erythropoietic cells for ions, for hemoglobin synthesis to what? To be effective. Alright, pretty quick, let's talk about iron absorption and iron requirement. So iron needs to be absorbed in the body just like any other nutrient. You know, when we take carbohydrates, the absorbable form is what? Is glucose. When we take proteins, the absorbable form is what? Amino acids. When we take fats and oil, the absorbable form is fatty acid and glycerol. In the same way, when we talk of iron, we have an absorbable state and then states that cannot be absorbed. So the body will try as much as possible to convert dietary iron to the most probable absorbable state. So in our case, we have Fe2 plus, which is the ferrous ion to be the most hot absorbable state of the ion. So in food it is converted as ferric hydroxide and heme protein complexes. The absorbable form iron is found in food as the ferric hydroxide, and heme protein complexes. The absorbable form is in the phosphate. Absorption occurs in the GIT, specifically in the apical membrane of duodenal enterocytes. So mostly in the duodenum. Mostly in the duodenum. And that is where the absorption occurs. So first of all, it has to be converted into the ferrous state. Mostly dietary iron is ferric hydroxide, and it has to be reduced to what? To anything that has the ferrous state in it, so that absorption will be made possible. So there can be malabsorption. That malabsorption can also contribute towards iron deficiency anemia. You might be eating the appropriate quantity of iron, but then there would be a problem in what? In the absorption. And we have factors that inhibit absorption and also factors that contribute to absorption. So let's talk about it now. Okay, so promotes iron absorption, inhibits iron absorption. All right. So let's talk about factors that promote iron absorption. Okay. So we have heme ion, ferrous form, acids. So we can talk about ascorbic. That is why it's very necessary. It's very good for you to take vitamin C, especially when you have malabsorption of what? Iron. Then we have solubilizing agents. Then we have some physiological conditions that uses a homeostatic approach to ensure or to promote iron absorption. So those ones we have pregnancy, we have ineffective erythropoiesis, then we have hereditary hemochromatosis, then we have iron deficiency anemia. Okay, then when it comes to the reducing agents or those that inhibit absorption, we have the ferric form, that is the Fe3 plus. Then we have when there's excess iron. So this one will also be a homeostatic approach. When there is so coffee, so taking teas like coffee, etc., also inhibits iron absorption. Then also, since they are acids, alkalines, they also inhibit. Then decreased erythropoiesis. I think that way it's all right. So these are the factors that enhances what? Iron absorption. and these are the factors too that also inhibit iron absorption. All right. So heme iron promotes iron absorption, because remember, heme iron, the heme itself contains what? An Fe2 plus moiety. So therefore, when it's broken down to a more inorganic form, the Fe2 plus will be what? Will be released. Then we have the ferrous form. The ferrous form is directly Fe2 plus ion. And the moment we take the ferrous form, it is directly what? Absorbed and then circulated into the what? Into the systemic bloodstream. Then acids. So what acid does is that, if you could remember your redox reaction back in high school, realize that we have oxidation agents and then reduction agents. So what happens is that the acids are capable of what? Of reducing the ferric form, or the other non-ferrous form of ion, to what? To the ferrous state, or ferric ions to ferrous state. So once that reduction is done, the ion will be easily what? Absorbed. Then we have solubilizing agents, pregnancy, ineffective erythropoiesis, iron deficiency anemia. Then those that inhibit ion absorption, we have the ferric form, that is Fe3 plus, excess iron. So when there is a lot of iron in the body try a way to what? To ensure or initiate a homeostatic what mechanism, whereby the receptors, the apical membrane of the duodenal enterocytes, those that are responsible for the absorption of what? Of the iron, will be seized. It's a homeostatic approach. Alright. So that is it. And then who needs iron the most? So we talk about age is a factor, sex is also a factor, and physiological condition. So children mostly needs iron. Children needs iron as compared to adults. Then in sex, females need more iron as compared to men. And then physiological conditions like pregnancy, menstruation, etc. can also what? Ensure the need for iron intake. Alright. Now let's talk about causes of iron deficiency anemia. So we have chronic blood loss. When you have an accident and you begin to bleed, the more you are bleeding, the more you are losing what? Excess iron that is found within the hemoglobin. Remember, every hemoglobin too contains iron. So we can even say blood itself, it's a very good source of what? Iron. Blood. It's a good source of iron. So the more you lose blood, the more you lose iron. And then we have the dietary factors as well, deficiency. So if you don't eat properly, if you don't eat foods that are rich in iron, and if you don't take foods, like ascorbic acid, for instance, is responsible for the reduction of what? Ferric ion into what? Ferrous ion, for absorptive purposes. So that one too is very necessary. Then physiological conditions like menstruation, etc., can also what? Can also cause iron deficiency anemia. Okay, so we have um, certain foods that are responsible, or are rich in iron. So first of all, we have can talk about liver. Liver is very rich in iron. So foods. So liver is a better source of iron than other source like, let's say, eggs, dietary foods, and vegetables. Alright. So it means those who don't take vegetables, and then the others are also likely to get what? Iron deficiency anemia. Yes. It's not specific though, but we can say that these are the foods that are rich, especially the liver, that are rich in iron. Now, clinical features. We have painless glossitis, that is the beefy red tank. We have the angular stomatitis. We have pica. So pica is the unusual craving for food. Unusual craving. So you just feel like eating something, some soup or anything, like just unusual cravings to eat anything. unusual cravings to eat anything, that is pica. And then spooning nails, spooning nails, spooning nails. Then we can even talk about pallor in the conjunctiva. We can talk about pale skin. Of course, these are all general symptoms of what anemia. But those that are specific to iron deficiency, you see the pica, the spooning nails, the angular stomatitis, the painless glossitis, that's the beefy rectum. Okay, so these ones are clinical features of what? Of iron deficiency anemia. Now in children, talk about irritability, poor cognitive function. So if your child does not perform well in school, you know, he forgets things so easily. In fact, iron deficiency anemia could be one of the cause. Then decline psychomotive development. Man, I think you don't have to get your child, so deprived of iron, because it's not going to end well. Child will begin to behave what abnormally and be poor in class. In fact, I would advise everyone to give his child what enough iron, because it's very good. Iron is very good. Okay, now this is a very important part, the laboratory findings. Assuming we suspect someone to have iron deficiency anemia and we want to investigate, what are we going to look out for? So first of all, we do full blood count, and then we do iron studies. Iron studies. Okay. So under the full blood count, these are the things that we are expecting to find: mean cell volume or mean corpuscular volume, mean corpuscular hemoglobin or mean cell hemoglobin, then mean cell hemoglobin concentration, MCHC. So what we have to find is that all these parameters has to be reduced, especially the MCV and then the MCH. Remember, all microcytic anemia must have their MCV or MCH reduced. Their MCV or MCH reduced. Okay. And then when we do the iron studies, we are going to come across serum iron, total iron binding capacity. We are going to see ferritin, serum ferritin. We are going to see serum transferrin receptor. We are going to see bone marrow. Okay, so that will be it. Then we can also do other lab findings like bone marrow iron store, erythroblast iron, and HB electrophoresis. Okay, so serum iron will definitely be reduced because there is a deficiency in iron deficiency anemia. So we are expecting serum iron to be reduced. All right. Then total iron binding capacity must be raised. So this one is a compensatory mechanism to the reduced iron. It's the reduced iron. So once there's a reduction in iron, the total iron binding capacity is expected to be raised. So this is what you just have to know. When you see that total iron binding capacity is high, it means there is iron deficiency anemia. So it's a compensatory mechanism. Then serum ferritin is reduced. So serum ferritin itself has to be reduced, in the sense that the serum ferritin is actually the stored form of iron. So once there's a decrease in the stored form of iron, it means there's a deficiency in iron. Because if there are a lot of iron, there is going to be a lot of storage, definitely. Then we have the serum transferrin receptor raised. So right now we have less iron. So what are we going to do? What is the body's compensatory mechanism? Is to increase the number of iron receptors, transferrin receptors. So right now, let's say now total iron binding capacity is also the same as serum transferrin. You just have to know serum transferrin. So what happens is that the transferrin receptor what increases, so that it can take at least most of the what available ions that are around. Huh? So that is what happens. So that it can take most of the available ions that are around. So total ion binding capacity is increased. That is transferrin. So there are a lot of transferrin coming in to bring the body iron. The body needs iron urgently. So what happens is that the transferrin what increases. That's the total ion binding capacity what increases. So they are searching everywhere in the plasma looking for what they have any available ion. Then when they get them, they'll come directly to the cells to what to deliver the iron to the cells. So the cells too has to get a lot of what iron receptors. That is why iron receptors too has to be raised. So it's a homeostatic what mechanism. All right. Then HB electrophoresis is normal, of course. When we want to talk about HB electrophoresis, then it means we have to talk about thalassemia. It's a thalassemia that we are going to deal much more about the HB electrophoresis. That's the we'll go much into genetics. Alright. Okay, so the last thing we would want to talk about is the dimorphic films and bone marrow iron. So dimorphic, the word means two morphology. Dimorphic. Alright. So dimorphic, two morphology. So what do you think will happen in dimorphic films? Okay. So this is when iron deficiency anemia, IDA, is associated with folate deficiency. So for instance, someone who suffers iron deficiency anemia has been transfused with the blood of someone who has vitamin B12 deficiency. What do you think will happen? So the microcytic hypochromic cells that we are looking for, cells that we'll be looking for in the blood film comment, will not be available. So here we will see cells with two morphology. We are going to see both microcytic hypochromic cells, and then we are going to see both macrocytic hypochromic cells. So that is how come the dimorphic film what is seen in patients. So either we have those that have gotten, so the conditions that is available for us to see dimorphic film is recent. We can talk about recent blood transfusion, then we can talk about recent blood transfusion. Then we can talk of okay, so let's say bone marrow therapy. Recent bone marrow therapy. Alright. So this is the basic things we have to know on iron deficiency anemia. Of course, if you have this in mind, there is no way you can miss any iron deficiency anemia diagnosis. You are going to get it right, straight on point. Alright. So thank you for joining us in this session.